So we will review some problems with regards to resonance here. This is worksheet 5 that goes along with our note on resonance. So we'll look at the first problem. It says a narrow plastic pipe is almost submerged in a graduated cylinder full of water, and a tuning fork is held over its open end. So I know I have a closed tube now. The pipe is slowly raised from the water. An increase in loudness of the sound is heard when the pipe is raised 17 centimeters. So this would be your L1. And then again, when it was at 51 centimeters, this would be L2. So it says determine the wavelength of the sound produced by the tuning fork. So we know that L1 is equal to 17 centimeters. We have this formula Ln equals 2n minus 1 lambda over 4. Again, that is the one for closed tubes. Just looking at our formula sheet, we have closed and open, and that would probably be the most important thing to make sure you're aware of. So if L is equal to 1, it's 2 times 1, take away 1, which is 1. So it's lambda would be equal to L1 times 4. Again, solve that just by putting in 1 for the n. Lambda is equal to 17 centimeters times 4. .68 centimeters would be the wavelength. So if the pipe continues to be raised, how far from the top of the pipe will the water level be when the next increase in loudness is heard? So L1 was 17 centimeters. L2 is 51 centimeters. So we're looking for the next one, which would be L3. So L3 is equal to 2 times 3, take away 1, I have 68 centimeters over 4. Again, just using this equation and putting in 3 for n. 2 times 3 is 6, take away 1 is 5, times 68 centimeters. So the next one should be heard at 85 centimeters. So this problem is for length. It doesn't really mention anything about frequency in the question, so I am just using the L equations for length. So let's look at number 2 now. The first resonant length of an air column resonating to a fixed frequency is 32 centimeters. So L1 is 32 centimeters. Determine the second and third resonant lengths if the column is closed at one end. So we have closed. So essentially we're going to do the same thing. We're looking for L2 and L3. We need to solve for wavelength first. So basically we'll use the same expression that we used up above. Lambda is the first length times 4. So the wavelength is 128 centimeters. Again, this relationship is only true for closed tubes. So then for L2, it's 2 times 2, take away 1, times lambda divided by 4. And for L3, it's 2 times 3, take away 1, 128 centimeters divided by 4. So for L2, it would be 96 centimeters. This is 5 times 128 divided by 4 would be 160 centimeters. So find the wavelength is your first thing that you have to do. Then use the wavelength in your length equations. Again, it does mention the word frequency, but it doesn't give you any values for frequency. So you are just going to continue using what we've used above. So we're going to do exactly the same thing, but with an open tube. So we will make the assumption that L1 is still 32 centimeters. We have to solve for lambda for an open tube. So for an open tube, it's Ln equals n lambda over 2. So Ln equals n lambda over 2. So let's put in L1 would be equal to 1 times lambda over 2. Lambda would just be L1 times 2. Lambda would be 32 centimeters times 2 is 64 centimeters. Now what we have to do is we just have to solve for the other parts of it. So L2 would be equal to 2 times lambda over 2. So L2 is 64 centimeters. So the 2's will just cancel. L3 would be 3 times 64 over 2. And that's equal to 96 centimeters. So again, this question just looks at what's the difference between a closed tube and an open tube when finding those fundamental lengths. And they really work the same. There's no need to find frequency. Those equations are obviously related to this, but it's not asking for frequency, so there's no use to use those Fn equations. So question 3 says, determine the resonant length of a closed air column resonating to a tuning fork, a little typo there, is 95 centimeters. Determine the first and second resonant lengths. So note that it's third. So we know that we have L3 equals 2 times 3 minus 1 lambda over, it's closed, so lambda over 4, which obviously would have affected the first part as well. So solving for lambda, this is 2 times 3 is 6, take away 1 is 5, would be equal to 4 times L3 divided by 5. Just rearranging this. Equals 4 times 95 centimeters over 5. So 4 times 95 divided by 5 is 76 centimeters. So now that we know lambda, we can use our other equations. So L1 for a closed tube would be 2n minus 1 lambda over 4. Let's just plug it in. 2 times 1 is 2, take away 1 is 1. Times 76 centimeters over 4. So 76 divided by 4 is 19 centimeters. We do the same thing for L2. L2 is 2 times 2 is 4, take away 1 is 3. Three times 76 divided by 4 is 57 centimeters. And that is how we look through and do those length questions. So number 4 says the second resonant length of an air column open at both ends and resonating to a fixed frequency is 64 centimeters. Determine the first and third resonant lengths. So every single time we just need to find lambda. So it's open. So we know L2 is equal to 2 times lambda over 2. So again, I'm just using this equation where I plugged 2 in for n, and which makes it 2 over 2. So that basically is lambda. So when we rearrange, we basically just say L2 is equal to lambda because it is open. So lambda is equal to 64 centimeters. So it's sort of a roundabout way of telling you what the wavelength of the sound is. So L1 would be equal to 1 times lambda over 2 equals 1 times 64 centimeters over 2 equals 32 centimeters. And that would be L1. And we're looking for L3 now. 3 lambda over 2. 3 times 64 over 2 would be 96 centimeters. That would be L3. Again, it's pretty much the same template to all these questions we've been doing already. Find the wavelength and then just plug it into the equation. The biggest trick, I guess, would be making sure you recognize whether it's open or closed. Number 5. A particular organ pipe, open at both ends, needs to resonate in its fundamental mode with a frequency of 128 Hertz. The organ has been designed to be played at a temperature of 22 degrees Celsius. How long must the pipe be? So, we have our first question regarding frequency. So, the temperature of 22 degrees Celsius just tells me I need to calculate the speed of sound. So we use this equation that we've learned. Giving me the speed of sound. We know that we have the universal wave equation, so the speed of a wave is equal to its wavelength times its frequency. So the wavelength of the wave, of the sound, would be equal to the speed of sound divided by frequency, 344 meters per second, divided by 128 Hertz. Means the wavelength of that sound is 2.69 meters. So again, it's the same approach. We still need to find wavelength first, and then we use it in the equations. So L1, for one that's open on both sides, would be n lambda over 2. L1 would be equal to 1 times 2.69 meters divided by 2. So the pipe would have to be 1.34 meters long. If this pipe is closed at one end by a stopper, at what fundamental frequency will it resonate? So again, now we're just saying it's going to be closed at one end. So let's just do with what we were doing. L1 is equal to 2n minus 1 lambda over 4. L1 is 2 times 1 take away 1. So 1. Wavelength over 4. So we're going to use this length in our equation. So lambda is equal to 4 times L1. Lambda is equal to 4 is 1.34 meters. Lambda is now 5.37 meters long. Using the universal equation again, assuming the same speed of sound as above, we get 64 hertz. Again, we would assume that the pipe is exactly the same. That would be the assumption. But again, identify whether it's open or closed. So number 6, we start to move and look at frequencies. So an error column open at both ends resonates with a fundamental frequency of 256 hertz. So F1 is 256 hertz. Determine the frequencies of the first and second overtones. So because it's open, we have the equations here. So based on the number of which overtone you want, so put in 2, you put 2 in for n, you just multiply the fundamental frequency by n. So 2 times 256 hertz. And that's this first overtone, or this F2. F3 would be 3 times 256. Would be 768 hertz. Maybe F3. So this would be your fundamental. This is your first overtone, and this is your second overtone. How that pipe works. So number 7. A bugle is essentially a 2.65 meter pipe that is open at both ends. Determine the lowest frequency note that can be played on a bugle. So, once again, open at both ends. So, using the exact same principle as we have above for open tubes, so this is just L1, so all I'm using is this equation where 1 is in for n, and then I'm solving for lambda by multiplying both sides by 2. Just that's where that equation's coming from. So lambda is equal to 2 times 2.65 meters. The wavelength of that fundamental sound will be a 5.3. The frequency of the sound will be equal to the speed of sound. So we're going to assume 22 degrees Celsius because we haven't really been told in the question. which just puts it at 344 meters per second. So let's assume 22 degrees Celsius, and that's just an assumption that we'll make, which is more or less where room temperature is. Over the wavelength is 5.3 meters. 344 divided by 5.3 is 64.9 hertz. Determine the next two higher frequencies, so the first and second overtones. So the second one will just be double the first, and the third one will be triple the first. So the first overtone is 129.8 hertz, and the second overtone is 194.7 hertz. So 130 will be F2, 195 hertz will be F3. So that's again looking at open tubes and how we calculate the first, second overtones. The one thing just to remember is that the first overtone would be F2, the third would be F3, the fourth would be, the second would be F3, the fourth would be F5. That's just one of those things that you just got to be aware of, that if we're asking for the first overtone, it's actually the F2, not F1. So number 8 has us look at a trombone, which again would be basically an open air column. So its first harmonic would be 87.3 hertz. Determine the second. Well, F2 would be equal to 2 times F1. So the second would be, the first overtone would be 175 hertz. If the speed of sound is 344 meters per second, again, that's the number we will assume anytime we're not given it, what is the length of the tubing being used? So this is the first time we're going to use this equation. So it's open at both ends, so there's our fundamental frequency, and there's our first length. So we're going to use this equation for the first time. So F1 is equal to the speed of sound divided by 2 times L1. And the only thing that changes if it's a closed tube is this ends up being a 4 instead of a 2. So rearrange for L. L1 would be the speed of sound over 2 times the fundamental frequency, 344 meters per second, 2 times 87.3 hertz. Equals 1.97 meters. The reason that this would be difficult to play is simply that that's 2 meters long that the tube would have to be. So the slide would have to be out almost all of the way, or very, very far. So that takes us to number 9. 2 tuning forks of frequencies of 512 and 518 hertz are sounded at the same time. So this is talking about the topic of beats, because those frequencies are very, very close. It says, what would you hear? Well, because of their near proximity, you would hear constructive and destructive interference oscillating or cycling. So you would hear a pattern of loud and soft sounds. We'd hear beats, in other words. And the frequency of those beats, or the oscillation, will be the difference in the frequencies. So in this case, it would be 6 hertz, which is part B. So F beat is equal to the difference in the frequencies. So we use absolute value bars. So we ignore any negatives. Be 6 hertz. A 440 hertz tuning fork is sounded at the same time as a 337 tuning fork. How many beats would be heard in 3 seconds? So again, I think I have a typo here. Let's make this 437. That'd be too far away. So at 437, how many beats would be heard? So I'm just going to put the biggest one first. So the beat frequency would be 3 hertz. The number of beats we'd hear would be equal to the beat frequency times the time interval. You should hear 9 beats. So number 11 is a very good question with regards to beats. A trumpet player sounds a note on her trumpet at the same time as middle C is played on the piano. She hears 10 beats over 2 seconds. If the piano's middle C has been tuned to 256 hertz, what are the possible frequencies of the note she is sounding? So anytime we have frequency, even though it's beats, it's equal to the number of cycles divided by the time you were listening. So we hear 10 beats in 2 seconds. So the beat frequency is 5 hertz. So that would be F2 take away F1. Now, let's make F1 256 hertz. And the question now is, what is F2? So F2 really has 2 possible answers. It's going to be one of those 2 things. So to figure out 5 hertz, if the beat frequency is 5 hertz, F2 is either above or below 256 by 5. So it could be 251 hertz, or it could be 261 hertz. So you actually have 2 answers here, 251 hertz or 261 hertz. And the way that you would pick between the 2 of them would be the one that the frequency that you know adjusted higher slightly if you can. And if the beat frequency drops, then that means that you went in the right direction. It would be the higher of the 2. If the beat frequency got faster, so bigger than 5, that means you went the wrong direction, and it would be 251, and that's how you would pick.